Hello everyone, my name is Konrad from DIVA.EXCHANGE. This here is the presentation held at MoneroKon 2022 in Lisbon, and we have done a re-recording of this presentation to improve audio and video. This here is a co-presentation together with two researchers. They have done research at the Lucerne University of Applied Science and Arts in Switzerland. And the title of this presentation is The Results of the Research. And they were trying to de-anonymize I2P network participants. Since DIVA.EXCHANGE is a fully distributed exchange for cryptocurrencies, it's especially interesting how their work relates to swaps, also involving Monero. Now, first, a few words about DIVA.EXCHANGE. We're a not-for-profit organization and open association based in Switzerland, so everybody can join and help us to develop the fully distributed and private exchange for digital values. That's why, by the way, we're called DIVA. It stands for Digital Values. And we're just a bunch of loose bunch of developers and researchers. So please feel free to join. It's free to join. You're going to learn a lot. What we do is, as we said, we create a fully distributed and totally private exchange. And since it's fully distributed, there is no business model involved. In a distributed world, this is pretty pointless. What's the agenda of this presentation? It's the intro, so you are here, and then I'd like to talk quickly about the project status of DIVA.EXCHANGE. Then Marco and Brian, the two researchers, are going to present their work, and we're going to have a short outro, and if you do have questions, you can ask them over social media. The scope of DIVA.EXCHANge is, as I said, to build a completely distributed and totally private network of own banks. So DIVA.EXCHANge is banking technology, free banking technology for everyone. Why is it free? Because the license itself is HEPL version 3, so it's a true open source license. So the code and all the stuff is truly free. The lowest level, and this is also a very interesting level, is I2P, which is a private overlay network. And on top of this, we have the DIVA chain, which is a blockchain as a PBFT implementation. It's no coin involved. It's Byzantine fault tolerant. On top of that, we do have, so that's what we call storage. On top of that, we do have a user interface, and we call this user interface DIVA. Now, once you install this stack on your own computer, never forget, if you don't have the keys, you don't own the values. So everything which you install with DIVA is totally local. There is no central entity involved in running your own free bank. As soon as you did that, you join the I2P network, and your stack implements the business logic of being your own bank. Now, what we did as developers in the past, we created an I2P SAM library, which is now quite popular. You can look at it in the Git repositories at GitHub or Codeberg. We also developed DIVA chain, which is a complete new blockchain which works over I2P, and we believe it's one of the only one which really works over I2P. So that the metadata which is involved in banking technology is totally private. We did this from scratch. Then we developed the DIVA protocol, which is the banking logic, so the exchange logic, the business logic. We do have a UE prototype called DIVA, and we Dockerized everything, so that's quite easy for developers to get started. Where we are is that DIVA chain works really stable, which was hard work to make it work over I2P. I2P as a total private overlay network is quite challenging to implement applications on top of it, because there are quite some network challenges to solve, and we did that. And we had a very smooth experience with Monero, so with the backend. So, for example, to implement transactions towards Monero nodes, which are running also locally, obviously. Same is true for Bitcoin or for Ethereum. And we do research together with Swiss universities. Currently, we're doing this with 3. One of the very important partners is the Lucerne University of Applied Science and Arts in Switzerland. Our next challenges are things like we want to do the swaps with Monero versus Bitcoin versus Ethereum and some other coins to prove how DIVA chain works. So this is what we're working currently on. And we're doing additional research because we're very skeptical people, and the things which is truly important to us is quality. So if we're not running a destructive approach and trying to destroy our own works, we can't trust ourselves because we don't like blue sky scenarios. We're really skeptical. So we're trying to do great research and difficult research on our own implementations and also on stuff like I2P. Now, please, let's have a focus on I2P, and I'd like to hand over the presentation to Marco and Brian, the 2 researchers. DIVA itself is DIVA.EXCHANGE is only the research partner, so we're not interfering with the results. The Lucerne University of Applied Sciences and Arts is looking at the quality of the research work. That's really important to us. Now, following the teaser video where the 2 researchers have produced, and then the presentation of the research results. Thank you.
Welcome, I am Brian.
Hello, and I'm Marco.
Welcome to our presentation about trying to de-anonymize I2P network participants. Our research title was to try to de-anonymization of participants of the I2P-based trading network for digital assets. We are 2 students from the Lucerne University of Applied Science and Arts.
A few words about the depth of this presentation. The presentation will be simplified, meaning there will be a trade-off between profound and understandability. So if you want to have more information about our research, or if you want to read into our research, you can read our paper. It's open source. You can read it on our university's portfolio database. We will cover here on this presentation only the main scope of the research, which is primarily one attack we've researched, and the focus is on the I2PD client, which is the C++ implementation from our research, but it's also applied to the I2P client, which is the Java implementation. A few words about the problem from our research. As there are many services who store the P32 address of its participant in the I2P network, the P32 address is like the address of all the participants inside the I2P network. There are many services to store this, like for example registry services, or also DIVA.EXCHANGE tries to do this. And many of the storages are public available. So our research problem, or the question of our research, is it possible to infer the IP address from those stored P32 addresses? Because if this would be possible, then there would be a highly privacy problem through the whole I2P network.
For a better understanding about what I2P is, we will give you a short introduction. I2P stands also for the Invisible Internet Project. It is a decentralized and distributed peer-to-peer overlay network like Tor. There are multiple implementations of the router, like the Java or the C++. And its main goal is to provide security for the anonymization from the communication for the source and the destination of each participant. What is I2P node? To understand what the goal at hand, you have to understand what I2P isn't. I2P does not try to disguise itself if you are a participant of it. There are parts of I2P that are centralized, like the receipt server, which there are about 13 at the moment, which are used for bootstrapping.
Another really important part for understanding I2P are the tunnels, because tunnels are used in I2P to de-anonymize the source and destination from each other, so that they don't know who the exact source and who the exact destination is. Here on this example, you see Alice and Bob. Alice is trying to send a message to Bob, and Bob is sending a request. You could also imagine as if Alice would be a normal client and Bob would be a web server. Here you see the tunnels. They are unidirectional, meaning there are separate tunnels for sending and receiving traffic. As you can see, if Alice wants to send a message to Bob, Alice sends a message through her outbound tunnel to the inbound gateway from Bob. There it goes to the inbound tunnel from Bob. Bob proceeds the message and sends the answer through his own outbound tunnel into Alice's inbound tunnel back to Alice. And also a key part for making possible that the de-anonymization is happening is that the participants don't know their position. The outbound gateway, the gateways and endpoints, they must know their position, because they have to proceed the messages depending on where they are. But the participants won't know where they are. For example, the participants in the outbound tunnel right after Alice don't know that he's in this tunnel. It could also be, or he could also think that he is in the outbound tunnel from Bob or somewhere else. So this is a really key part from these tunnels and how they make the anonymization possible. Some other interesting facts is that default length is 2 to 3 hops, and default amount from tunnel are 2 in and 2 out, and tunnels for sending and receiving messages. And another key part for our attack is that the tunnel renewal is 10 minutes, meaning that every 10 minutes the tunnels are renewed, meaning if all the participants are available, the tunnel will be renewed for another 10 minutes, so all the participants are in there. And if another participant isn't available, he will be replaced, but the available participant will be taken over into the next tunnel.
For a full understanding, you also need to know what the NetDB is. NetDB is a distributed network database that is used inside of I2P to share informations between each node. It is a distributed hash table which is based on the Cut-Miller algorithm. The NetDB inside of I2P mainly has two information stored. These are the router infos and lease sets. A router info contains informations about individual routers, especially the IP address and the port on which the router is connectable. Also, there is the lease set. A lease set contains a set of router infos, how another service, a B232 address, is reachable. These are router infos which also contain the tunnel IDs of the in-gateways which you should connect to if you try to reach this service. The lease set contains the information about the in-gateway of an inbound tunnel. In this example, if Alice tries to reach Bob, it's gonna look for the lease set of Bob and will find information about multiple inbound gateways for Bob, which it sends then its data to.
Now a few words about the attacks we've driven. We analyzed multiple P2P attacks, and it's really important to know that no malware injection was involved in all our attacks we covered. We only tried to attack the protocol itself, meaning there was no manipulation other than on our own clients. All the participants we want to connect who aren't in the control of us weren't touched and weren't manipulated. And all our attacks were covered on a theoretical level, meaning we started to build a test network for attack simulation, but because this was a highly complex topic, we couldn't finish the test network for attack simulation. So we covered the attack on a theoretical level, meaning more research is later needed, but from a theoretical standpoint, those attacks seems to work. And now about the main scope of our research. This was a tunnel takeover, which mainly is a combination from a Sybil and intersection attack. A Sybil attack, for people who don't know, is an attack where you try to flood a network with own manipulated routers and trying to get a majority or part of a majority or network and trying to influence its behavior. And an intersection attack is where you try to go inside a tunnel and intersect the tunnel there. And in a nutshell, or about what the following attacks is about and is really important to know, the attack we will cover is about mass attacking a network. So meaning we're trying to not to de-anonymize one router in particular. We're trying to make an attack on a whole network and try to figure out who we can de-anonymize and who not, but without any specific target in mind. And the attack is based on statistical probability, meaning there is no 100% guarantee, but repeating the attack will increase its probability. And also, very important, the attack we will present is about figuring out the position of the participants inside the tunnel, because as we covered before in the tunnel explanation, participants don't know their exact position. But if they know their exact position, then you can de-anonymize a target, because if you know that you control the first and the last hop inside the tunnel, then you only would need 2 participants or 2 routers inside the tunnel. But since the participants don't know this information, this isn't possible. So we tried to find out a way to figure out that we control the first and the last hop, and this is how we did it.
As Marco already explained, with the tunnel takeover, its goal is to take over a tunnel of a target. In the example shown, we try to take over an inbound tunnel of Bob. Normally, if you would just have all of the participants, you had already the anonymization of Bob, because you would see the complete traffic, not the inside of the traffic, but where it is going. Our goal was to show how we can do this with not having to own all 3 of the routers, or if you would have longer or shorter tunnels, all participants. The main idea was to get at least 2 participants inside the tunnel. This is the first one, the gateway, and the last one. This is because of 2 reasons. Of the 2 reasons that the last one, the participant in the shown example, knows the IP address of Bob, because it has to send the traffic it receives, the data, to Bob itself. Normally, it doesn't know that Bob is the endpoint, but this is the goal of this attack to get hold of. Every information we gather, we have to send to a server where the known informations are getting analyzed and set together, so we can be sure that we have the anonymization of the target. The evil gateway is needed because it's the first entry point, and we know of Bob. That means the gateway is already known, and it's easy to see if we have control over this participant, because it's known its role, and if we have luck or we find another way how to position it, that it's pretty easy to see. Now the other way, the way to get the last participant is to see if the gateway sends, if the communication between the gateway and the evil participant is with the same middleman. All these informations are sent to an analysis server, where they are analyzed, and we try to recreate the tunnel. If we see that evil gateway and the evil participants are communicating with the same middleman, we can hope, because we do not have 100% guaranteed that it really is the same tunnel, and that we have a tunnel overtaken. What now we can do on side of the client, with a reverse lookup of the lease set, I can try to find the B32 address of Bob, and so find and look for our own gateway we control, if it's inside the lease set, if we know that, and the information from the evil participant of the IP address, we can try. We have with some luck, we have find Bob's IP address and B32 address. As explained, with the lease set and the whole tunnel taken over, or parts of the tunnel, and the router information from the evil participants, we have the anonymization of Bob.
Now, after we figure out this attack, we try to get some information from this attack and try to figure out how we can mitigate this attack, and how different aspects and different parameters from the different resources who are involved in the attack can be mitigated, and how they influence the whole situation. So we tried to mesh all this information into a formula, which is seen here. I won't go into detail of this formula because it's really complicated, but if you're interested in how this works, it's explained more in our research paper. But with this formula, it's possible to plot such nice graphs like this, where you can get some really useful information. For example, here we tried to figure out how the tunnel lengths influence the infiltration rate of tunnels. For example, here we could calculate or figure out that longer tunnels will mitigate this attack, especially this special kind of attack. And if you can see, there are if you have a tunnel length from 2 or 3 hops, you're already pretty neat covered, especially if an attacker tries, simple attack where it tries to take over 10 or 20% from the network. But if you have a 2/3 majority, meaning he has control near of the same network, it will take a lot more tunnels for delivering this attack. Meaning more tunnels equals better mitigation against this attack, especially because it's harder with this kind of attack for an attacker to figure out that he has control over the last participant inside the tunnel. Another thing we can show here is that more tunnels is meaning that an attacker has more possibilities to make this attack. Because, for example, if one participant has double the amount of tunnels, the attacker will have double the amount of tries for this special tunnel configuration.
An alternative for tunnel takeover aspect of luck to have the participants in the right position is to combine it with a DDoS attack. The idea behind this is to flood and target the participant of a tunnel, so it doesn't get used in a new renewal of the tunnel. This is especially useful if you already know the B32 address of a service. The first step you would do is identify the inbound tunnel. This you can do with the lease set of Bob. There you can see all of the gateways and the tunnels there are, and pick one of your choice. The next step would be to do a DDoS. This can happen via if you just send too many requests. Just one thing you can do, and this is a part of I2P, is that you send a lot of tunnel requests to this router, and with on a specific threshold, the gateway will not accept any other new tunnel requests again until the threshold is going down. This you will have to repeat until your own tunnels your own routers are at the right positions. And if you have some luck, like we have in this example, the last one, the evil participants were already there because we have a Sybil attack in place, so we had only just had to DDoS the gateway until a router from our own set of participants was there. As mitigation steps, there would be to use longer tunnels, because especially for the DDoS attack, this would make it harder to take it over, and you would need more participants inside the tunnel to have all the informations you need for that de-anonymization. Another way would be to have less tunnels. This is problematic because at the standard, in the default settings, there are only used 2 per pool. This means if you would only use one and one would drop out, you have no backup, and the connection to I2P would be less stable. Another one would be have 2 variable tunnel lengths. This would mean that for each tunnel, the router would decide to use more or less participants. This would have less impact on the network because not all tunnels would have to be longer, but it would also increase, it would make it harder to guess how long a tunnel is, because you do not know as an attacker. That means if you think you have the 2 right participants, if you have a tunnel of 4, a 50-50 chance there is another participant, or there is really Bob. So you have to have extra work to be sure that your attack was successful.
And for a conclusion, our main conclusion was that the I2P network is resistant against most or nearly all common attacks, meaning the I2P community did a really great work for figuring out various mitigation against all the different attacks possible against P2P networks like I2P is. This was also the reason why we only could cover theoretical attacks and not practical. So, meaning for most people, I2P is a really viable option. But what we also figured out is that de-anonymization with an I2P cannot completely be ruled out because some high complex attacks, as shown before, are still possible. Our main two attacks we covered in our complete research was the two correlating route inside a tunnel, like the one attack we've showed you before. There is the main mitigation against this attack from I2P is that you don't know where the participants are positioned, so you have to figure this out, which is some kind of a more or less strong mitigation. And another attack we covered in our research, but not in this presentation, is traffic analysis on ISP or even state or possibly even interstate level actor, where you try to figure out the flow from I2P traffics and try to de-anonymize a target like this. Their mitigation is some background noise from I2P and also trying to make it as hard as possible for injection, meaning packages can be injected any other flags and the packet size from the tunnels are always the exact same size, making it harder to figure out where traffic will flow. But the main conclusion from our research is that more research is needed, because as more research as will flow into I2P and also other overlay network, as more resistant against other attacks it will be, and as more usable and more viable is it, and as more people are using I2P and more research, the better it will be. Thank you for your attention.
Thank you, Marco and Brian, for these insights into your research work. Now back to DIVA.EXCHANGE. I'd like to introduce you to the code base, which is on GitHub, mirrored from Codeberg. There you find all the AGPL version 3 licensed source code, which we produce at DIVA.EXCHANGE to produce the fully distributed and private banking technology for everyone, so feel free to join there. Please use Codeberg if you do have issues, because this is our main repository. At MoneroKon 2022, we had as a giveaway the so-called Dilemma elderberry syrup with us, which got picked up by the community very nicely. There was a Monero tag to pay a few to pay a bit to the developers of DIVA.EXCHANGE at the bottom of the bottle. So thank you very much for your donations, and please feel free to donate some Monero to us to appreciate our work at DIVA.EXCHANGE, or simply join our association, or even better, commit some code to our repositories. Now, we called, by the way, this elderberry or this elderflower syrup dilemma because we see lots of dilemmas in the area of privacy, especially the dilemma of not having a business model where we're absolutely happy with it, but others seem to need a business model to produce fully distributed exchanges. So, for example, this is an interesting dilemma. And everyone in the community will have its own views on how to solve that. The same is true for privacy and for communication. There are quite some dilemmas around. Last but not least, if you do have questions regarding DIVA.EXCHANGE or regarding the research work we're performing, please feel free to contact us over social media. There is Mastodon available, there is Twitter available, there is a Telegram channel available called DIVA.EXCHANGE chat. Please join us on Telegram, on Twitter, or also on Mastodon to talk to us. Thank you very much for your attention. Have a good time.